Hi there, class. Welcome back. This is Mrs. Brunk again, and we're going to continue our look at triangle congruence, and we're going to learn another shortcut today. So remember in yesterday's class, we learned about the ASA congruence theorem. So we learned about ASA, which meant if in two triangles we could find two pair of angles that were congruent in the two triangles, and the side that was between those two angles were also congruent in the two triangles, then it was enough to prove without a doubt that the triangles were congruent. So again, that was the two angles and the included side. Now today we're going to be looking at a second shortcut, so a shorter way than showing all six parts of the triangles are congruent. It's called the SAS. Okay, so this time see there's two S's and an A. And the order again of how that's written is important. This means two sides and then the angle between them. In other words, two sides and the angle that they form. In two triangles, if they're congruent, then the triangles are completely determined by that information and must be congruent. Okay, so the side angle side congruence theorem says if two sides and the included angle of one triangle are congruent to two sides and the included angle of another, then the triangles themselves are congruent. It means every other part would also have to be congruent. So what that might look like in a situation like these two triangles is, let's say I knew these two sides were equal. So I mark them congruent. And let's say these two sides were congruent. And so I had marked them congruent to each other. And then let's say I could go in here and I could show that these angles right here were congruent. If that was the case, then I would have enough information to use the SAS. Okay, because you have two sides and then the angle that's between them. It's like the two sides that make that angle. And if you think about how that would work, if you have two sides and they have to be a distinct length, and then they have to make a certain degree angle, then there really is no other way to complete the triangle because you already know the length of the two sides and then the angle that they form. So that's the new shortcut for today. So we're going to be exploring that a little bit. We'll look at verifying if triangles are congruent using this, and we'll also look at some things that, some proofs that would involve using this theorem. So let's look at our first example. So we're going to just go through and see if we can verify that we can use this. So I've got, and remember it's really important to be marking your drawings as you identify parts that are the same, to mark them the same. And so if you look at the two sides that, there's two sides that are both 74 inches in these triangles, okay? And there's also two sides that are 46 inches. In this triangle right over to the left, we've got an angle that's 37, and we've got a 37-degree angle in this triangle. And in both triangles, they're in the same position there. We've got the two sides and the angle that they form. So that would be SAS. And you can see we have the same thing in both. We have two sides and the angle that's between them, SAS. So if I wrote a triangle congruent statement, I could say something like triangle, let's say we start with L, so let's say we say triangle LJK. Then it would be congruent to triangle, well, L corresponds to P over here, so that would be P and then MN. Okay, so however you start and name the first triangle, then you just have to make sure you name the second triangle in the same order. So since I started on this side, let's see, I went from L to J, then over here I had to go from P to M. Okay, does that make sense? So just make sure when you're naming them in this corresponding order. And also then we state, this is by the SAS congruence theorem. That's how we abbreviate that. Okay. So let's see if we have enough to satisfy in this one. Okay, so in this one, we've got a side that's 2.5, a side that's 2.5. So we can mark those congruent. We've got a side here that's 1.7, a side here that's 1.7. And then they already have the markings on these angles that are in between them, G and D. Now they gave us another piece of information here in this triangle. It's kind of irrelevant. It's really unnecessary. We've got all we need now. We've got the 3 parts, and they are side, angle, side, right? So 2 sides and then the angle that they make. So again, you can see that these sides that I just marked equal, see how they come together to make that angle? Okay, that's why that's called an included angle, and that's because it's the angle that's formed by those 2 sides. So we again can write a statement that says that these triangles are congruent. And so you just decide how you want to name the first one. So let's say I call it the first one EDF. So see, I went along this side. I went from E to D to F, right? So now I'm going to do the same thing, but I have to go from H to G to J, right? So H, G, J, and they are congruent. And again, by the SAS congruence theorem. Okay, next one. So we've got this side that's 20 here, and we have a side over here that's 20. So I can mark those equal, right? All right. We got a 20 and a 20. Okay. Then we've got this side here that's 19. Well, here's the one that's 15. I don't see one over in the other triangle that's 15, but that's okay. We'll see if I get enough. This one's 19. This one's 19. Okay. So let's mark those congruent. And then we've got an angle here that's 43. But this one over here is 45. So that was the angle that was supposed to be congruent. So we can tell right now these are not congruent. This is enough information to show not congruent. Now sometimes you just won't, like, you might not have conclusive evidence that they're not congruent. You just don't have enough to support that they are. Like, you haven't gathered enough evidence yet. But in this case, they definitely are not congruent, because the angle that should be in that position, the angle that should be formed by those 2 congruent sides should be congruent if the triangles are congruent. So we know these are not. So again, you can use the theorems as well to, you know, gather and give evidence that triangles are not. Okay. Now sometimes you'll get triangles that there's no actual measurements listed on them at all. Okay, but that doesn't mean we can't prove they're congruent if they've given enough information that is already up front given, and then things that we can know for sure by other theorems that are things that we've learned, properties that we've learned. And in this next one, you can see they've already marked a pair of sides congruent here, right? And they've marked a pair of angles congruent. So we've got a pair of sides and a pair of angles, which would be like SA or AS, but we need a third thing, right? And there's nothing else marked, but these triangles are connected, right? They're connected along this side, and that's a side that they both share. And we know that there's this thing called the reflexive property, and reflexive property says that if that something is always congruent to itself. So I'm just going to label that on here. If I was writing a proof, I'd actually have to use this reflexive property, right? So I'm going to mark that, and now I've got enough because I've got that order of the parts, side, angle, side again. So there's side, angle, side in the triangles. Oop. And this particular diagram does not have vertices labeled, so we'll just say they're congruent. The triangles are congruent. And by side, angle, side. So we can't actually write a congruent statement here because we don't have vertices to do that. Okay, so we've got a couple more that are very, very similar. So we've got sides marked equal here, angles marked equal or congruent here, and see they share a side. So that's side, angle, side, and side, angle, side. So notice it's in both triangles, it's the 2 sides are the ones that make that angle, so the 2 congruent sides. So this, see over here and there, and then they make that angle. And once again, in example F, okay, so we've got 2, both congruent by the SAS. Okay, and again, congruent by SAS. So there's not a lot of things that you can just tell by looking at a diagram that are congruent. You can always prove that shared parts are congruent. Just like, in the last lesson, we could always tell that vertical angles were congruent. There's not a lot of things like that you can just tell by looking at it, but because there's not a lot of absolutes, but absolutely vertical angles are always equal. Absolutely shared parts are always congruent. So things are always congruent to themselves. So it's like a free part when we see that. Now in these next questions, they want us to give what additional information we would need. Now we may not have the tools or the theorems or whatever to support that at this point, but what would we need to be able to prove these triangles are congruent? So looking at this first pairing, I've got a pair of sides already marked congruent. You can see that, right? So we've got these sides and these angles. So if you wanted to use SAS, you're going to find out later on, once we learn all these shortcuts, there's lots of different other pieces of information that would help us prove these congruent. But right now, in order to use SAS, we would need to know the side on the other side of the angle, right? So that we had that SAS. So we would need to know, I'm not going to mark them, I'm going to highlight them. So we would need to know that BC was congruent to HG. That's what we would need. And we don't know that, so we're just going to say we need this. That's what more we would need to prove congruent by SAS. Now how we would find that, we couldn't do it just by looking at it. There's no way to tell. But if we were given more information, if say these were connected along that side or whatever, we might be able to then prove if we knew those two pieces of information. Okay, and then similarly on the next pairing, we've got two pair of sides though this time, and we've got, in order to use side angle side, we'd have to know the angle between them. So we'd have to know this angle right here and this angle right here. So we would need to know angle X was congruent to angle K. We would need to know, that X and K were congruent. And then we would have SAS. Okay, so following the pattern in the last lesson, we're going to now take a look at writing some proofs that triangles are congruent. And they're really not a whole lot different than, what we've been doing with these, just looking at the drawings. We're sort of just going through a checklist of information that we're given and seeing if we can establish enough to use SAS. Well, we actually now know ASA and SAS, and if we could establish either one of those, that would be enough. And so we won't always now be using SAS. There's still now ASA, and then once we learn more and put more in our list of shortcuts and ways to do this, then we'll have more and more different ways to prove triangles congruent. But in this particular problem, we're told it is given that BD is the perpendicular bisector of AC. Okay, so we know that BD is perpendicular to perpendicular bisector of AC. So in this drawing over here, we know, if I wanted to, I usually like to label everything, so I'll just say I use the symbol perpendicular bisector and then of AC. That way if I look at the drawing just at a glance, I'll know, oh hey, that thing is perpendicular to AC and also cuts into equal parts. And that's it. That's all they give me. That's not a lot. In fact, they did not give me a single part that's congruent. So that means in my proof, I have got to have 3 statements that prove parts of these two triangles are congruent, because I have to list in there some place in the proof specifically those are 3 parts that satisfy either ASA or SAS. So first of all, I know that if that thing is the perpendicular bisector, I can say, and you can tell that they've already written the statements, that AD is congruent to DC. Now, I usually like to put the segment symbol over top. But I know that those are congruent, and I just marked them on the drawing, right? And that's because we know by the definition of bisector. So you could say definition of perpendicular bisector, definition of bisect, I try to shorten it up as much as possible. So bisector means to cut into equal parts. So I just put definition of bisector. So we got one part, right? There's one. We need 3. So we've got 1. And we need 2 more. And so then they go on to say, well, angle, let's see, BDA. So here's BDA. BDA, that's this angle, is congruent to BDC. Oh, that's the other angle over there. And those are both right angles, right? So we talked about this yesterday, that there's different ways. You could say, definition of right angle, or you could say something like they're both 90 degrees. But the theorem is actually called the right angle congruence theorem. So symbolically, this would be the way we could write that. So we're up to 2 parts, right? So there's 1, there's 2. We got 2 parts. We just need to get a third. And the final statement before they are able to prove the triangle is congruent says BD is congruent to BD. Well, that says the same thing. And you're right, it does say the same thing. That's because that is a shared side. And we know anytime we say something is congruent to itself, that's reflexive. So that's actually a reflexive property of congruence. You could just say reflexive, that's fine too. And now looking at our drawing, we have established that 2 sides and the angle between them are congruent. So I like to do that. I like to label the S and the A, and then it'll come in handy later on when we have more ways to do this, because when you label a side with an S and an angle with an A, you can see the order that it's supposed to be in, because we're going to learn some other ones. Like we're going to learn one that's called angle angle side. So that's different than angle side angle, and we're going to learn side side side, and then we're going to learn others. So it helps when we can just see it right there on the diagram. So that's the SAS congruence theorem. Okay. Let's look at a couple more. So I don't know about you guys, but this diagram right away on this next proof just jumps out at me as, I don't know, I hope you train yourself to just automatically be seeing vertical angles here. We have these triangles that are open and away from each other. I see I'm going to be able to get some vertical angles, and I'll just see what else I have. So I'm going to take a look and see what they've given me, and then I'm going to come up with the reasons that each of these things is either given or must be true, so that I can prove these 2 triangles are congruent. And it says that CD, so this one right here, bisects AE. And it also says that AE bisects CD. So we know these are both bisectors. They bisect each other. So maybe I'll just do something like this and like label, let's say, bisect each other. And I know it says it there, but I just think when I look at the drawing, and I can put bisect each other. I can't, my stylus isn't working today very well. So actually we got a 2 for 1 then, because I mean, even if I didn't see this, and if they hadn't written these statements in the proof, I would know right away that if they bisect each other, they cut each other into equal parts, I would know that this segment and this segment are equal, which is the very first thing they said. So of course step 1 is, the reason is given, right? Step 2, they said that AB is congruent to EB, and that's that definition of bisector. Okay, we're told it's the bisector, and we know bisecting means cut into 2 equal parts. And then they said CB and DB, and that's this pair. And same reason, right? So we could put, like, say, the ditto marks or rewrite that. So from that one piece of given information, we got 2 parts, and we know we need 3, right? And remember I was saying this drawing right there just kind of spoke to me, and I saw the vertical angles right away, right? And you should be able to kind of just start picking those out. So it says that angle ABC, which is this angle right here, is congruent to this angle right here, EBD, and we know those are vertical angles. So that's the vertical angle theorem. So we're up to 3 parts. The 2nd through 4th lines show me my 3 pairs that I want, right? Those are three parts, right? And specifically, they go in this order, 2 sides and the angle between them that they make. See how that's the angle, and then that's the side. That's side, angle, side. So side, angle, side. Okay. So what we're going to do is we're going to make this one be a you try question. And so I want you to give this one a shot. pause the video, give this one a try and fill in your reasons and mark your drawing. And you can tune back in, and I will share the answers with you so that you can gauge where are you at with proofwriting. And this will wrap up our lesson at the end of this you try question. So go ahead and give this one a try, but be sure to tune back in and check to see how you did. So pause the video now. All right, thanks for giving that one a try. So this one was nice because they actually gave you 2 parts already in the given, much better than the other 2 proofs, especially the one above it where we had to come up with all 3 parts. They gave you 2 right up off the bat, and those were the first 2 listed statements. And then all we had to do is use that reflexive property because they had a shared part right here, right? They had a shared side, so that we knew that had to be congruent to itself. And I'm going to put these segments, these should have been on here, segment signs. And that means we use side, angle, side. Okay, so that does it for today, and I'll see you in class.